Look at the hardware running our world today. What used to require an entire building has collapsed into structures that are now practically microscopic. Computing evolved rapidly from room-sized mainframes to desktop units, eventually resulting in the smartphones we carry today, devices with more processing power than the systems used for the Apollo missions. This physical contraction has reached a point where we can embed processors into everyday objects. Streetlights, shipping containers, and home appliances are being outfitted with sensors, creating a category of hardware known as smart things. This graph illustrates how this transition occurred. As the green line tracks the physical miniaturization of these components, the cost to manufacture them drops at a similar rate. This intersection makes it financially viable to deploy millions of sensors at once. The combination of minimal physical size and low production cost provides the industrial foundation for the Internet of Things. The Internet of Things is a project to link the physical and digital worlds. As shown in this diagram, the objective is to take physical objects and map them to virtual counterparts using a communication network. We have already solved the naming convention for this project. The rollout of the IPv6 protocol provided enough unique digital addresses to theoretically tag every object on the planet. However, a technical bottleneck remains in the connection itself. Cellular networks are optimized for high-bandwidth activities like streaming video. That architecture requires high power consumption and expensive hardware, which is unsuitable for a sensor that only needs to transmit a few bytes of data. These sensors have unique physical requirements. They may be installed underground or within concrete walls, and they must operate for up to 10 years on a single, non-replaceable battery. Achieving a global network of connected objects requires a connectivity model designed specifically for these low-power, high-range constraints. The technical response to this connectivity problem is the Low-Power Wide Area Network, or LPWA. LPWA networks allow for tiny data transmissions over very long distances. Because the radio hardware consumes very little energy, it enables the decade-long battery life required for industrial sensors. Demand created a fragmented market. This flowchart shows private companies developing closed systems, like Sigfox and LoRa on the right. Relying on this patchwork of incompatible networks prevents hardware from communicating, causing severe security and interoperability risks across city infrastructure. Reliable, large-scale infrastructure cannot function on a patchwork of private systems. It requires universal, open standards. To resolve this fragmentation, several international bodies intervene to set global standards. This list identifies the key organizations involved, including the Third Generation Partnership Project, or 3GPP. 3GPP defines the technical specifications for global cellular networks. This includes the specific protocols necessary for massive-scale IoT infrastructure. 3GPP standardized two protocols to compete with proprietary systems, LTE-M and NB-IoT. These standards were designed to broadcast directly into the cellular tower infrastructure that is already deployed worldwide. Because these technologies are standardized, telecom operators can support billions of sensors using their existing hardware, ensuring a secure and unified connection across different countries. By establishing these universal rules, 3GPP provided the technical framework necessary to integrate digital intelligence into the physical world. This standardized connectivity is the primary driver behind the transition to the smart grid, the updated electrical infrastructure for the 21st century. Look at the top half of this diagram. It shows the traditional power grid, which is a one-way system. Electricity flows from the power plant to the consumer, but there is no data flowing back to the utility. The bottom half of the diagram illustrates the smart grid. In this model, there is a bidirectional flow of both electricity and information. The utility receives real-time data about usage and load from every point in the network. This awareness requires millions of hardware points, such as this digital smart meter. These devices, along with sensors on transmission lines, act as the data collection points for the entire grid. The reliability of this massive network is entirely dependent on standardized LPWA connections established by 3GPP. When the grid is connected in this way, operators can integrate renewable energy more efficiently, reduce maintenance costs, and improve overall system reliability. The successful operation of this infrastructure relies on the secure data exchange protocols maintained by 3GPP. While telecommunication standards are often abstract, they have a direct physical impact on daily life. They determine how we manage energy and how reliably our cities function. The technical specifications written by 3GPP provide the operational framework for the modern world. They are the rules that allow the physical systems of the 21st century to communicate.